Good afternoon, everybody. Maybe someone could just confirm that you can hear me.
Yes, we can hear you.
Thank you so much, Emily. All right, perfect. Well, good afternoon and welcome to the first event in the NRIC Tech Talks series. We're going to use the Tech Talk series to dive into the details of some of the projects and technologies that NRIC and others are working on that we think could help innovators have successful demonstration projects and even beyond demonstration projects. So I'm thrilled that we can start today with digital engineering because I think that this is one of those pivotal technologies that can help nuclear deliver on budget and on schedule, as well as help NRIC work seamlessly with innovators and even in the future streamline the regulatory process. So I'm really excited about digital engineering, but someone who is even more excited about digital engineering is Chris Ritter. And now I'm going to take a few minutes to introduce Chris, who will be your host for this Tech Talks today. Christopher Ritter is the director of the Digital Engineering Center of Excellence and the group lead with the Digital and Software Engineering Group at Idaho National Laboratory. He currently leads digital engineering on the Versatile Test Reactor, the National Reactor Innovation Center, and NNSA Digital Twin programs. His expertise is in software engineering, software development, leading software teams, systems engineering, software integration, and database management. Before coming to INL, he was Director of Software Development at Spec Innovations in Manassas, Virginia. He served as the Chief Architect of InnoSlate, which is a popular systems engineering tool that leverages elastic cloud technologies and AI and natural language processing for high scalability and advanced analytics. He architected the software system and consulted on the data ontology for a centralized mission risk management system for the Joint Staff at the Pentagon, and supported Marine Corps business process reengineering for its capability portfolio management processes. He was also a computer programming teacher at St. Michael's Academy in Warrenton, Virginia, and developed an elementary school computer programming curriculum. He holds a bachelor's degree in computer science from Virginia Polytechnic Institute and State University. So Chris has experience at the highly technical end of this, as well as teaching to elementary school students, which I didn't realize before, but that makes a lot of sense. So let me go ahead and hand it over to Chris Ritter and ask him to keep the dialogue somewhere in between elementary school and the highly technical, if you would, Chris.
Thanks a lot, Ashley. Yeah, we'll do our best to stay somewhere in between that balance. So we're excited today to talk with you about digital engineering. So first, a few housekeeping items. So please see the link in the announcements that were sent to you that will take you to the individual breakout sessions. If you can't find that, you can also obtain all webinar links directly on the NRIC website, which is nric.inl.gov. Additionally, I suggest keeping questions and answer panels open during the entire webinar, which also in the publish section will have the link there for you as well. So please ensure your audio and visuals are turned off when you're not speaking if you are a panelist. And when you're returning to the main event, the best way to rejoin the main event is by clicking the leave button on the breakout session and then clicking the rejoin button on the main event. If you're unable to rejoin this way, please remember that you can find all webinar links once again at nric.inl.gov. So next slide, please. Oh, there we go. Okay, so first, what is digital engineering? So the Department of Defense defines digital engineering as embodying a deliberate transformational approach to the way that systems are designed, engineered, constructed, operated, maintained, and retired. So with digital engineering, what we're really trying to do is we're trying to transform people from using Word documents and PowerPoint documents for engineering to a model-based paradigm. And we'll go over what that means here in a minute. We're trying to integrate the data across the system's lifecycle through a digital thread. So basically, we're trying to take all those different siloed databases that you're used to seeing with different teams and make it so there's basically autonomy between those different systems. And then we're trying to analyze the system as a whole during design or operations using artificial intelligence and machine learning and multi-physics codes to make that possible. And so that is a very transformable approach, which we think can make a huge difference to the design of nuclear reactors. So this is new for nuclear, but not new for DoD. So DoD is the ones that developed this original digital engineering strategy that we've kindly borrowed. And so the Air Force is a little ahead of us, right? And so the Air Force announced literally just a few months ago that they're about 10 years ahead on development on their new stealth fighter, which is incredible, right? 10 years ahead of schedule, right? Usually they're 10 years behind schedule, right? But we're 10 years ahead of schedule through digital engineering technologies. But to add to that, it's not just in DoD. In the construction world, we've seen Mortenson Construction able to save 600 cumulative scheduled days using virtual design and construction, which is a part of digital engineering. And some of those ideas were actually utilized to build the DoD digital engineering strategy. And then thirdly, we've seen General Electric realize $1 billion cost avoidance using digital twins. So this is truly a technology that can drastically change our landscape here in nuclear. So if we go to the next slide, we'll talk a little bit about how we map our strategy at NRIC to the strategy at DoD. So on the left there, you'll see that little bubble, and that's the Department of Defense digital engineering strategy kind of main tenets. So the first is the use of models. So what is a model, right? To me, a model typically, right, means a diagram or some kind of visual representation that's then persisted to a database. So for me, what I really care about, right, is that what you're using is built into some kind of data model that we can then integrate to other tools and other systems across a quote unquote digital thread. So that brings you to point 2, which is that authoritative source of truth. So it's not a single source of truth, right? We're not trying to say you have to use one tool or one platform to design something, but the idea is there's a place that all the data ends up, and all that data is connected together. And that's that whole idea of a thread, if you can think in your head, right, of like a little spider web, right? And you want to have the ability that all that data is integrated together in some kind of web across. And you can query across it and you can do analytics. The third tenet is incorporating technological innovation. And so I think that's something that as a national laboratory, we do pretty well. I think a lot of universities, which I'm sure are on the line today, do very well at that as well. And so making sure we don't forget that. One thing we don't do well sometimes at INL is realizing those innovations to be used in the engineering field. And so that's something we really want to make sure that we accomplish through digital engineering. So the fourth tenet is establishing an infrastructure and environment to host these tools. So that's something personally coming from commercial industry, right, that is easy to take for granted, right? Keeping an environment that's secure so we can design these advanced nuclear reactors is non-trivial, right? You have to support expert controlled information. You might have to support, we'll call it sensitive information. And you also need to enable the ability to run these codes in high performance computing settings, right? And all that is pretty difficult actually to set up. And then the fifth tenet is the transformation of your culture and workforce to use these new tools and paradigms. So at NRIC on the right, this is how we've decided to apply these technologies. So we've started for models with model-based system engineering. So we'll talk about that on the next slide more in detail, but MBSC is the idea that we're going to throw away the documents and we're going to move to using system models like systems modeling language or lifecycle modeling language to design our systems at the system level. We're also at INL using building information management technologies and product lifecycle management technologies in other places, which will eventually get incorporated to NRIC as well. The second thing that we're working on at NRIC is the digital thread idea. So actually, I'm happy to say that NRIC recently open sourced a lot of the software we use to make this possible. So if you go on GitHub and you search Idaho Lab, you'll see our development live as we're working on building out our digital thread to enable these new test beds. Tenet number 3 is digital twin. And so that's the technological innovation we're trying to incorporate, right? So we're trying to apply those technologies to our test beds and our new reactors. And we have a number of projects in that space at INL today. And then the fourth tenet, how we apply that is with cloud and high performance computing technologies. And we'll go over that in more detail in a second. And then the fifth, which we won't talk about in detail today, is through our Digital Innovation Center of Excellence, or DICE, which is how we get our culture transformed inside our own laboratory and externally. So that's kind of a community of practice to see these ideas through our entire laboratory as a whole. Because NRIC, we're one team, but we need to see these innovations throughout the entire lab, because as NRIC, we rely on many different groups and teams to be successful. So if we move to the next slide. So model-based system engineering. So this is actually my main domain expertise before coming to INL. And so MBSC, you can see there on the bottom left, that's a functional diagram. So that's actually an action diagram out of LML, or if you're familiar with SysML, it's very similar to a SysML diagram. And what that does is that shows there are boxes and lines, right? But those boxes and lines mean much more than that, right? So each box in that diagram actually has an object or a piece of data behind it, right? That we can link to from other tools and other databases. Also, that diagram is executable. So what does that mean? Well, it means you can actually run a simulation directly from that diagram and check your logic. You could generate your schedule and your costs for your nuclear reactor plant. And then up there on the top right is a physical diagram. So that's an asset diagram, or if you're familiar with a block diagram, it's like a block diagram, right? Once again, boxes and lines, right? We're just trying to show physical things, and then what's the link between that physical thing and another physical thing, right? What's the interface that we need? And that's all we're trying to capture. But what's unique is, once again, those boxes and lines are all persisted to a database, right, that then are linked together. So those functional diagrams and those physical diagrams will be actually linked together through different data elements. And then what we're trying to do is link those across the lifecycle, right, to other tools. And then on the bottom right, you'll see a set of requirements, right? So requirements are also integrated in here as well, right? So you generate these functional and physical diagrams to then generate these different requirements throughout the lifecycle. And so we've really emphasized a lot on using functional diagrams first, and really thinking about what's the functionality that your test bed or reactor needs to accomplish, and then deriving your physical architecture from that. And so, a functional first paradigm, kind of typical system engineering 101. And then these system models are linked to our requirements repository, and then we're trying to integrate these across different teams. And so we have a cloud environment, which we'll talk about a little bit more in detail, where both our laboratory, government, and industry teams can all collaborate securely through a cloud environment. So they're actually in the same tool infrastructure, and we actually have the ability where you can be in separate projects and separate data access while at the same time linking what we call cross-project relationships back and forth. So a pretty cool way to design new nuclear reactors. So if we go to the next slide. So building the digital thread. So buzzword, right? But that just means we want to connect things, right? Remember the spider web I mentioned earlier, right? And so, so digital engineering, we are right now focused primarily on linking CAD, which is computer-aided design models, to those model-based system engineering models. And so, so you see this diagram on the right, and there's a lot of boxes and lines, and you don't have to read it in detail. But the idea, if you look at those top swim lanes, right, is requirements management, functional analysis, system architecture, linked to your 2D, 3D world. So typically in the system world, right, you'll build a block diagram, you'll build an internal block diagram, some kind of block diagram, right, to describe your physical architecture. But you want to take that and you want to make sure it is linked to your 2D P&IDs and your 3D models. Why does that matter? Well, often your design's going to change and it'll get inconsistent between your 2D models and 3D models in the physical space and in your system space. And that can be a big problem. And that is where you derive what we call silent errors through your design. And you certainly don't want those because those silent errors ripple, right? So if I change a requirement and forget to notify the CAD designers who forget to notify the test procedure writers, then over time, right, that's a debt, right, that I'll have to pay during construction. It could be a 10x cost difference or a 100x cost difference, depending how bad it really is. And so that could be a big problem. The second thing we're doing is we're trying to generate automated reports. So I mentioned we're throwing away the documents. That's not 100% true. So we still use documents, right, quite a bit, but we generate all the documents automatically from these tools. And so, so we use those as our NQA1 artifact still, but we are automating that process. We have them produced in the typical document template. And the nice thing is too, all the documents are consistent. They look really nice because they're automatic. And then we're integrating this entire approach with our overall digital engineering ecosystem. So NRIC uses the same tooling infrastructure as the Versatile Test Reactor program, as the NNSA digital twin programs, as a number of other programs within the Nuclear Reactor Sustainability Project. So all those different integrations that we're not building are we're going to inherit through what's called deep links. And we'll talk about that more in detail in one of the digital ecosystem sessions. And our overall plan is to integrate this entire capability with operating facilities. So we can enable a full digital twin of our test beds at NRIC, but also for industry at large. So if we go to the next slide. So digital twins. So what is a digital twin? So there's, I think, different people have different answers, but this is my answer of what I think a digital twin is. So digital twins to me represent the merging of the digital thread idea, right, connecting the data, control theory, artificial intelligence, and online monitoring into a single cohesive unit, right? So all that is integrated together, and it's a virtual model of a physical asset. So one thing I think that sometimes people misunderstand is, in my opinion, a digital twin, you must have a physical asset that exists. You can have a virtual twin, but that's not a full twin yet until you've integrated to your physical plant. And so here on the right, this is a virtual twin. This is a Safeguards by Design digital twin project, which has an NRIC integration. This is how ultimately I think this technology will get deployed to analyze a reactor through its multiphysics codes, which generates simulated operational data to look for reactor misuse or diversion. But that technology, I would argue, is not a full twin yet until we're able to connect it to a physical plant. And so enabling that bidirectional communication between your physical infrastructure and your virtual infrastructure is super important to realize that technology. In the digital twin breakout session, if you're interested in this tech, there is a talk about Magnet, which is producing a full twin of a test bed here at INL. And so if you're interested in this, I highly suggest you to attend that breakout. So we'll go to the next slide. So the fourth and final tenet I'll talk to you about is cloud and high performance computing. And it can't be understated how difficult it is to get a cloud environment that's secured at the level that you need to be able to support nuclear reactor design information. And so what we've done at NRIC is we've enabled a single sign-on environment. So for all of our tools, whether you come from a contractor or you come from INL, you can actually use your home organization authentication to log in. So what does that mean? That means there's no username or password to remember. You go hit a URL, we have an agreement with your IT, and you click your company name and you're automatically logged in. And so there's a lot of security reasons that is superior, but it's also just a lot easier. The inertia, right, to using these digital tools has been reduced. The environment is secure. We support official use only and export controlled information as well in the environment. We have a hub and spoke deployment model. So INL as a whole is our hub, and that monitors all these spokes like NRIC to make sure that everything is kept secure through the design process. And we're working on an interconnection to our high performance computing environment. So you'll be able to, in theory, run your multiphysics codes, for example, on Sawtooth, our HPC environment in DOE&E, and then connect that to our cloud environment. So that you'll have the ability to kind of seamlessly go between both worlds. So NRIC as a whole, right, we have access to the 3 different HPCs that INL offers from Sawtooth, which is 5.6 petaflops a second, Lemhi, and Valken, which are about a petaflop a second nominally. So, so that connection we're really excited about, and that isn't something we're working on at NRIC, but it is one of those things that we get to inherit as being a part of the overall ecosystem. So with that, I'd like to move to the next slide and introduce Peter Suyderhoud. So Peter started working out as a system engineer at a large engineering, procurement, and construction contractor on nuclear-related projects at the Hanford site and Oak Ridge. He now works in the digital engineering group with a specific focus on model-based system engineering. Peter is working on a number of different MBSC projects. I talked to him before this. I think it's like 5 different MBSC projects that he is supporting these days, including the Versatile Test Reactor program and our MCRE project at NRIC. And he's supporting several other Gen 4 nuclear reactor projects at INL and through NRIC programs. So without further adu, Peter.
All right, thank you very much. So I know Chris kind of went over it real quick, but and apologies to any other systems engineering literate people on this call, but I kind of first wanted to touch on some theory before we dive into things. So if we go to the next slide, the first concept, the next slide, is systems thinking, which kind of sounds straightforward and simple at face value, but we've found is quite often overlooked in our engineering world. And it's really a holistic approach to analyzing complex systems and processes that really focuses on the way a system's components relate to each other, how a system functions within the context of a larger picture, and how we can understand the patterns that cross disciplinary fields and areas of application. So what does this actually mean? Well, there are a couple of key pieces. The first one is that this methodology focuses on how things work instead of how they look. So Chris mentioned, we're focused on the process versus the structure first. Another key piece is the interdisciplinary nature of this framework. As engineers, we tend to silo ourselves in our areas of expertise, do what we're comfortable with. But what we're really after using the systems thinking concept is to collaborate and encourage communication at sort of the overall, I'll call the plant level, the whole of the project before proceeding further into the project, the detailed design, and returning to our specializations. So this concept really establishes the framework for executing our digital engineering scope within NRIC. Next slide. So now that we have a quick introduction to systems thinking, we can jump into sort of systems engineering, which is the application of these systems principles to complex engineering projects like nuclear design. It's important to know the distinction between system engineering and systems engineering, or a system engineer and a systems engineer. Terms that get thrown around a lot on engineering projects, but system engineering really focuses on the design of a particular system within a particular discipline. So an electrical engineer working on the design of an electrical distribution network, or an INC engineer working on the design of a particular control system. But with systems engineering, we're really focused on this, again, this interdisciplinary nature of the framework, while also applying sort of a structured process for design and realizing this final system. We'll go to the next slide. So now we get to talk sort of how this process actually works. One of the most effective tools for conveying this process is called the V diagram, which I've sort of mocked up here. You may have seen this diagram before, but the real intention of it is to show a process that prevents us from starting straight on the detailed design. You know, sometimes there's a natural tendency of us engineers, but sometimes it's driven by schedule, cost pressures, right? We need to get a cost estimate out as soon as possible, right? That's going to drive us straight into detailed design and ignore the plant as a whole. But how this process really starts is, you know, we start in the top left corner with eliciting our top level business stakeholder requirements, whatever you want to call them, that touch, you know, a host of disciplines and require a lot of systems to work in concert together to achieve the intended goal. You know, typically we try to keep these functional in nature, you know, that the plant needs to do something like produce power, right? Once we have these set of requirements and functionalities, we can start to outline the concept for how the system will behave, much like concept of operations and what types of systems we can expect to see in our integrated design. You can see that the steps actually have feedback loops, which is sort of the recognition that, you know, projects aren't always straightforward, and a lot of the time downstream activities can sometimes cause us to reevaluate decisions or requirements that were made, you know, previously in the design. And if, you know, we keep driving down the left side of the V towards the bottom, we start developing system level concepts through requirements and functions that overall systems, you know, things composed of many components and performing an integrated function have to perform. And then so once we've uncovered all of our functions, right, we're ready to start synthesizing an architecture, how it looks and what it contains. You can see the process continues all the way down to the bottom once we've defined all our components and how they all look, behave, operate. Coming back up the right side of the V, we're starting to confirm that the design meets our requirements through a process called verification. Sometimes we catch things that don't pass this inspection step that cause us to reevaluate our design process. So those are those dashed arrows coming across, and they feed back into our requirements and our design. But once we pass these detailed checks, you know, we sort of then do this integrated validation that, hey, our plant performs as we intended in our initial requirements and our initial functionalities. And then we declare ourselves, you know, once we pass all these final checks, now we're ready to operate. Next slide. Okay. So now that we see that there's benefit to this engineering process, we start to look at, you know, what does the actual application look like today? And, you know, as you can imagine, based on the preceding diagram, a lot of documentation is generated, and Word and Excel dominate the output of this process. Sometimes people start to use requirements management tools, but a lot of the times they're really just repositories for information rather than being the source of truth for establishing and analyzing requirements. And the requirements also tend to stand alone in these tools. So particular changes to a requirement have to be manually assessed throughout the rest of the requirements management database or the design to see, you know, what else it has to be evaluated for impacts. To move forward with systems engineering as the go-to process, we need a different framework that's more cost-effective and kind of less cumbersome. And at the next slide, we get to model-based systems engineering. And this is Chris introduced the concept, right? But it's really a concept of databases and models as the primary means of information exchange and as an up-to-date sort of working copy of the design instead of static documents. Because, a document by nature is officially out of date the minute that it's printed and issued. It's just a snapshot, which we can still accomplish through MBSC, but that's not really our focus during the design phase. Chris already introduced the concept of a model. It could be a simplified version of a concept or structure, graphical representation of a process, abstraction of information to facilitate understanding. There's plenty of different models that can be generated. But in this framework, the key is that these models form an integrated part of our technical baseline so that we can convey design information to one another and collaborate in the shared, typically cloud-based environment. Next slide. So the basic concepts of MBSC, you can kind of think of it as a kind of a big scatter plot of a bunch of dots in space, right? And each dot is called an object, and objects can be requirements, systems, components, risks, actions, any systems engineering data element, right? But they're not just, floating things in space. They also have, supplemental attributes behind them. So, think of these as adjectives. A person has attributes like hair color or height, right? A system has, or a component has attributes like size and capacity. And then also, these dots are related to one another. Imagine in that little diagram I have there on the left is sort of a parent, right? And they would have established these parent of relationships to two children objects on the right. So sort of same holds true for all systems engineering data. We can define relationships between requirements, functions, risks, all sorts of different things in our design process. Let's go to the next slide. So how do we actually implement this in our processes? Well, we sort of focus on that left-hand side of the V diagram, that beginning. We add our requirements and high-level functions to our database, right, and establish relationships between them. Requirements satisfied by functions, decomposed by other functions. If I have a requirement to provide power, that functionality is added to its own object, right, and then decomposed to what it means for lower levels of the design. So I would need to produce heat, transfer that heat somewhere, convert that thermal energy to electricity. Next slide. And this process continues, right? Once we have a full scope on the handle of our functions, we can start producing diagrams and models that show how these functions relate to another. And that's sort of, I don't want to re-say what Chris already went over, but it's really executing these models. We can see how they look in real time and see how these systems will function before we get too far down the design road. So you can kind of see how the scatter plot I described is beginning to take shape, right? It's as more and more data is created, more links are established and the web kind of grows. Maintaining these links is absolutely important throughout our process so that we can perform, impact analysis. If I change a requirement, I want to see all the things in my ecosystem, my database that are impacted. Next slide. One other element to this is that we can start integrating aspects of project management. So just like I can track requirements, I can track action items, I can track schedule, dates, I can track costs, I can track technical decisions so that if I ever want to see, why something is a certain way, right, I can always trace it back through these relationships established between objects back to those decisions or that cost or something in my database. Next slide. And then there are some, other random SE activities facilitated by this, system validation. My models can prove that my system will function as required. I can also prove that my requirements have met in the design and print out like automated reports from the database that proves that they do, right, through relationships I've established. And I can also identify like all systems or functions that I've included in the design and credit it to defend, the project against identified risks. So on the last slide, we get to talk about the challenges. So, perhaps there's some value to this process and this capability, but why isn't it more prevalent in the industry? Why haven't more organizations employed it? And, it does come with its share of challenges, right? One of the biggest is organizational resistance. As engineers, we're very comfortable in our domain, but shy away sometimes when asked to learn new concepts outside of our field of interest. Even the concept of systems engineering is a lot of times foreign and seemingly complex. And when you tack on, an MBSC tool, that sometimes tips the boat. Our goal in our group is really to be there in the early phases to help people learn the tool and the process, and then be there for technical support as the design progresses. We don't just hand off the tool and say good luck. Obviously there are some other big challenges, but one of the final challenges I'll leave you with is how this process of MBSC integrates with other engineering activities and disciplines. We don't want to. The intent is not to duplicate other work that other engineers are used to doing in their own tools, right? We want to provide a useful data set so that we can grab the information and go off into other design tools and finish the process. And with that, I'll segue into Brennan, who will talk more about our engineering collaboration environment and how we integrate these other tools.
Thank you, Peter. All right, so I'll introduce Brennan Harris. So Brennan is a simulation and full stack developer at Idaho National Laboratory, supporting our digital and software engineering team. He specializes in 3D modeling and code development for the web. Before joining INL, he was a multi-body simulation developer for Sentient Science Corporation, developing tools to create and inspect statistical surrogate models. He holds a bachelor's degree in mechanical engineering from BYU, Idaho. With that, Brennan.
Thanks, Chris. All right, so if we can go to my first slide, or slide right after the title slide here. So you have these giant engineering projects, and for me personally, when I see something that's built to this scale, it's kind of life affirming. Like, these are symbols of our ability as humans to come together and work together and make something beautiful. Maybe as if you're an engineering manager, you look at this very differently. You see this as like a lot of headaches, and there's just a string of human souls that had to be crushed to deliver all of this complicated stuff on time. I'm going to be talking about engineering collaboration specifically through engineering software, and hopefully discussing some approaches that ease some of the pain in working together on large projects with large engineering groups. Next slide, please. Okay, and if we can pull up the first, well, if we can just pull up all the content on this page. So we have, I've kind of broken it into two eras of engineering software, and yeah, well, these might not be perfect categories, but what I call the legacy era is when you have software and licenses and files that are on individual engineers' computers, on their personal machines. And then when you want to start sharing that work or those files, you have to kind of use some of the old school methods. I mean, what I'd call old school methods, like email attachments or shared network drives. And there's a lot you have to communicate as you share files back and forth. In the modern era, you have software packages where you have kind of a cloud environment, or you have software like an Autodesk environment or a Siemens NX Team Center environment, where the engineering data kind of covers a broad scope, and there's a lot of functionality there. But there's always this proprietary ecosystem, and private software developers obviously have an incentive to create a silo, like Peter kind of alluded to, where you keep buying products and you keep upgrading your licenses and you stay in that environment, which is great for small projects. But on these giant, large collaboration projects, you start to see maybe the drawbacks of that system, because you're not going to get every team and every kind of sub-team working on a subsystem, you're not going to get them all in the same environment. You're going to be contracting externally with different teams that use different software, and so there's some issues to overcome there. And then you have problems that are going to be problems with engineering software no matter what, which is you have sometimes cultural change. You have engineers that are used to the tools they're working with, or you have managers that have already kind of purchased a lot, spent a lot of time and money in getting a working system. And for some software guy like me to come in and say like, hey, I have something better, you know, that you managers, I know you have your logic, and you're right. There's not, there's a huge cost that sometimes you have to pay to start doing something new or to use new software. And so we're trying to think through approaches that overcome some of those hurdles, including the cultural ones. So if we can just move through the next slides kind of quickly. So our approach starts with having a central database with a strict kind of set of rules about the data that can live there. We don't, you know, if you're going to write a bearing or bearing data to our database, we want it to always have fall in the same category and make sure we enforce all the same data that's being recorded for that asset or whatever. Next slide, please. So the first thing we have to do to play in a system like this is extract the data, whether that's from a legacy system or an internet connected system, and make it available to the internet. So we're working on this with Autodesk products right now, extracting the data, making it available. Next slide, please. And so then once you have the data extracted, you can add it to the central database. Next slide, please. And what's really cool is once you have this process that you can keep adding sources of data, and there's some cost that you have to pay in getting the data into the database, but once it's there, it doesn't matter what the origin is because all that the structure of it is strictly enforced. So if we can look at the last slide here, our vision is that engineers and designers or other people who aren't engineers who are working on requirements, they mostly are just using the systems they're comfortable and familiar with. And then the collaborative utilities that are created are able to extract from this central source of data. And so if I'm one engineer and I create a cool viewer, if I can create it from the centralized bank, then I can share that viewer with everyone on the project. And they can just keep adding their data and keep going along mostly as they're comfortable with and according to management styles and software packages and everything. And this is one method that we're looking at for making manager happy collaboration. And I think that's it. Thank you.
Thank you very much, Brennan. So with that, we'll go to the next slide. I want to introduce our breakout presenters. The first is Brennan, who you just met. So Brennan and Taylor Ashbacher. So Taylor Ashbacher is the principal cloud architect for INL's digital and software engineering group. He's responsible for managing cloud infrastructure while developing compliance and protection of cloud resources. Before joining INL in 2019, he was the senior development operations engineer at First American, managing critical business infrastructure in the Amazon Web Services cloud. He holds a BS in computer information technologies from BYU, Idaho. So next slide. Our second presenters are Jaron Browning and Ross Coons, who will be talking about digital twins. So Jaron is a software engineer at INL in the digital and software engineering group. He leads multiple projects and initiatives that advance and utilize digital engineering technologies. He's additionally the digital thread pillar lead in the Digital Innovation Center of Excellence, allowing him to promote collaboration across INL and the efforts of digital threading. His expertise is in software development, system integration, digital threading, digital twin, system architecture, cloud computing, and cloud architecture. He holds a master's in computer science from Georgia Tech and a BS in computer information technology. Prior to coming to INL, he was a software engineer at Capital One. Ross Coons, Dr. Coons, is a statistician for INL's data and visualization environments and explainable artificial intelligence techniques. His explainable AI work focuses on the fusion of machine learning and physics technologies. He has developed a 3D visualization framework that allows emergency planners to simulate responses to various safety and security scenarios. His visualizations have been presented at the White House, and he is now being used by federal, state, and municipality leaders to plan for the expanded use of electric vehicles. He holds a PhD in statistics from Florida State and a bachelor's in statistics from Idaho State University. Before joining INL in 2015, he was a statistician for Michelin in North America. Our third session, on the next slide, is on the NMDQI initiative. So if you're into material science, this is the breakout session for you. We have 3 presenters in this session, and I will shorten the bios for time's sake. We have Alan Roche, who is a distinguished staff scientist at INL. He has a BS and MS degree in aerospace engineering and a PhD in mechanical engineering. Alan joined INL in December of 2019 after 20 years at Sandia. At INL, he's leading what we call the Nuclear Materials and Discovery and Qualification Initiative, or NMDQI for short, as we always call it. He started his career at PPG Industries in fiberglass research, was a technical staff member and manager at Sandia, where he worked in a variety of roles ranging from FEA codes to component design, testing, and manufacturing. He was Sandia's Bourne Qualified Grand Challenge Laboratory Directed Research and Development Project Lead with use of goal of additive manufacturing to change qualification paradigm for low volume, high consequence, complex parts that are common in high risk industries. One of our other presenters for this session is Andrew Slaughter. Andrew began his studies focusing on structural engineering while studying at Michigan Technical University and Washington State, where he got his master's. He shifted his focus for a PhD at Montana State, where he studied applied engineering mechanics and researched snow and avalanche physics. This work included extensive field, laboratory, and computational research and paved the way for him being awarded a National Science Foundation postdoc fellowship at Cornell University in 2011, where he focused on phase tracking snow microstructure models. He joined INL in 2013, where he is focused working on our Moose multiphysics environment. Our third presenter in that session is Zachary Prince, who's on the far left side. Dr. Prince is a researcher at INL specializing in numerical method development for reactor physics. He got his PhD in 2019 from Texas A&M, where he researched topics involving transient reactor simulations, deterministic transport acceleration, and reduced order modeling for reactor physics. Upon completion of his PhD, Dr. Prince began researching at INL, where he is focused on developing the Griffin multiphysics reactor framework for simulation of advanced reactor designs, and the stochastics module tools in Moose, which is interesting to hear about that hopefully in this NMDQI presentation. So he is one of the lead developers in both, and Dr. Prince has expertise in particle transport models, reactor physics, and large-scale system solvers, stochastic methods for sensitivity and uncertainty qualification. So with that, sorry for reading that quickly, but we're moving quickly here along. We invite you to join our breakout sessions. So if you remember, you should have an email in the announcement to join those. If you don't have the email, click the Q&A button. If you can't click the Q&A button, go to the NRIC website, and please join one of the breakout sessions now. So we are going to close out the main session, and we'll see you guys back at 4 o'clock Mountain Time. So let's go to the next slide on the panel discussion to introduce the speakers. So our first speaker is Michael Delamar. Michael Delamar has practiced system engineering for 38 years. His experience includes design and manufacture of satellite components at Hughes Aircraft, development, modification, and sustainment of the intercontinental ballistic missiles at TRW, and development of one-of-a-kind nuclear industrial facilities at Bechtel National. He currently serves as Bechtel's Corporate's Global System Engineering Workshop Chair and is a Bechtel Distinguished Technical Specialist. His responsibilities include defining system engineering and requirements management processes, developing the system engineering culture and training, and supporting system engineering implementation on select projects. Mr. Delamar holds a BS in physics from the University of California, Irvine, and a master's in system engineering from Johns Hopkins. He's also certified as an expert system engineering professional by NCOSE, and within NCOSE, Mike is the relationship manager with the ASME, represents Bechtel on the Corporate Advisory Board, or CAB, and is chair emeritus of the Critical Infrastructure Protection and Recovery SIPR Working Group, and former co-chair of the Infrastructure Working Group. Our other presenter is Jared Harper from TerraPower. He's a professional engineer with a bachelor's degree in mechanical engineering from Louisiana Tech. He's worked in multiple industries within his career, including pulp and paper, oil and gas, government nuclear waste management, and commercial nuclear power. He's responsible for the development and practice of system engineering processes at TerraPower in Bellevue, Washington. He managed company-wide efforts to integrate system engineering into the company's core engineering practices. He serves in multiple roles at TerraPower, one of which is the system engineer for the molten chloride reactor experiment project, or MCRE, as we call it here. His previous experiences include mechanical fluids design, field engineering, nuclear procurement engineering, and project engineering. So with that, we will go to Mike. Mike?
Thank you, Chris. Yeah, if we can go to the next slide, please. My first slide here is really just to give you an introduction to Bechtel for those of you who don't know who Bechtel is. It is a company that's over 120 years old. We got a long history in nuclear, and some of our current nuclear projects you might recognize are with the Vogtle units 3 and 4, where we're constructing those. We're also supporting the versatile test reactor and the Natrium projects. But we also have other business lines in oil, gas, and chemical. We have lots of projects going on around the world there, mining and metals as well, and building of various kinds of infrastructure, including railways, like you see there, or airports or other types of infrastructure there. Company is overall about 25+ billion per year or more, depending upon which year you're talking about. So with that introduction of the company, let me just go on to the next slide, please. So this is the INL folks did a really good job of introducing the topics of digital engineering, and so I'm not going to really rehash any of that. What I really want to just talk to you is a little bit more about what Bechtel is doing. And there, where Bechtel is really making a significant investment in digital engineering, where we have started with developing processes and looking at what we are doing today and how our processes work, and how would we do those processes in a digital engineering environment, with using guiding principles of systems engineering and requirements management and data-centric execution as being sort of guiding principles in how we would change our processes towards the future. We are identifying in those processes what data is required in order to execute those, and how that would flow through an environment. We're developing all the supporting services that go along with that, some of which you've seen, not our particular ones, but of the ones which similar to the ones that INL has been developing. In the core will be a digital environment like you see depicted here that provides the infrastructure, a common language, so an ontology that goes along with it, data repositories, enables exchanging among the tools here. And it's we're developing it to address all of the Bechtel's business lines that I covered before, those 4 business lines, and for the full life cycle. So if you're familiar with engineer, procure, construct, or EPC, we're covering that full life cycle. The work that we're doing will be also applicable to things like a front-end design or to a project management style contract. And using the approach that we have depicted here with that digital environment in the center, we can use any tools with a modern API once an integration is built. So if you look at those arrows and you say those arrows really represent an integration between the digital environment and whatever the number of different tools that may be represented there, whether it be for model-based systems engineering or doing the analytics or doing building information management or verification or procurement, all of those things are wrapped into this. And any of the tools that we have are going to be able to be communicating to each other through this digital environment. So that can be done with tools that Bechtel selected. So we'll be selecting tools that are that will be our principal things of use, or principal go-to tools. But it'll also allow us the flexibility to implement and incorporate into this and integrate customer-directed tools. It would require an integration to be built, but once that's done, it can be reused wherever. So like INL, we are using the lifecycle modeling language in our MBSC environment. Corporately, we've been employing that, and we're building it into how we deal with MBSC. And we've also implemented LML to some degree on some projects, primarily in requirements management, but that's One of the area where we are focusing in on the MBSC right now is on requirements management, the functional analysis aspect that was described earlier, and then building out of asset hierarchy so that you can allocate requirements and such. This capability is still in development, and we are planning incremental releases. So the next slide, please. So one of the things that I wanted to point out here with this, so you can see our digital environment in that yellow circle there. But the other element to this is how can we integrate with others doing nuclear work? So the idea here is that Idaho has put together these tools that are like deep links and the diamond ontology that can be mapped to our digital environment. These things are open source or available to others. So if nuclear providers use the INL solutions, we can build that integration to it. So it makes sense that if others are going to be using that we can build that integration. So our digital environment is a proprietary one, but it is one that that we can tie to others. And the deep links one would make it a ready fit. So that's my quick presentation of where Bechtel is heading in digital engineering. And with that, I'm turn it back over to Chris.
Thanks a lot, Mike. So we'll kick it over to Jared Harper to give the next presentation. And Jared has quite a few slides, but Jared will remind you the 7-minute kind of timeline. So Jared, over to you. Otherwise, Mike and I can answer a couple of questions while we wait. So maybe we can do a couple of those. So we'll answer one question while we wait for Jared to join. So one of the questions that came in, and I'll let Mike start with the answer to this, is the idea of adapting a better digital engineering ecosystem is easier said than done. What are you doing to overcome these hurdles, employee pushback, lack of experience to lead a digital transformation, and limited company budget? So, Mike.
Great question. I can answer this from what we Bechtel are doing. This is a major investment that is sponsored at the executive level, at the highest levels in the company. So there's a significant amount of investment that has been put towards that. Part of the activity in here to address the issue of the culture of the company and being able to accept this is that we do have a organizational change management thread to this. So that's a significant element in terms of trying to understand how to get that acceptance and to get people warmed up to it and the full breadth of trying to address that element.
Thanks, Mike. I know at INL to address those three things, so employee pushback, that's why we have our Digital Innovation Center to get everybody on the same page. There's many different ideas and many different thoughts, and so we use that as a way internally to get that transformation. The second thing is we try to pick tools that are not too challenging or too different than the way that people currently utilize their engineering world, right? So we try to pick tools that are easy to learn. And lack of experience to lead a digital transformation. So personally, that's why I was hired here at INL, was to do that. So pulling people from industry or other companies who've done this is something I would suggest. And limited company budget, that's true everywhere, right? We're all limited. So the key is making sure that your digital engineering and digital ecosystems are adding a value pretty quickly to a project, right? And then that cost becomes much smaller, right, when it's making impact right away. So Emily, was Jared able to join?
Yeah, I cannot get him to come off mute. It won't let me do it. I don't know if Lisa or Cheyenne are able to.
Okay. So Chris, I can add one thing about, when you talk about the talent to do it, one of the things that we've done is that we have an architect to the whole thing who has understood and worked in the area for a long time on how to do this kind of building up of services and building up of ontologies and building. So they got to have a fairly good understanding of the full breadth of that kind of work, and that has been a major important thing. Like you said, INL had hired you to help do this work. Our project to do this digital environment has brought on key talent to do various aspects of this, and particularly with one core architect.
So, so the next question, which we'll use to answer, is what types of projects are you currently using the digital twins approach on, and what type of platform are you using? So we'll start with Mike.
Yeah, okay, so digital twin we are doing to varying degrees. So like the kind of digital twin that Chris you were showing out there, we don't have one that is like an end-to-end project that's got everything on there. That said, there's a lot of things in terms of if you look at what is the digital twin in terms of its requirements. So we have some where we've captured requirements base for it, and some that of course we have building information modeling that is there. It's not tied to the physical facility, but it is used for the design element of it. So all the support elements of it for procurement, we have systems that deal with all that, and they have an integration among some of these. So we have, I wouldn't say we have achieved the full image of a
Your call has been forwarded to an automated voice message.
Go ahead, Mike.
Yeah. So but we have pieces of it currently deployed, not this whole digital environment or this new digital environment that we have.
Thanks, Mike. At INL, so a number of projects use these tools and environments. So we have this deep links technology, which Mike mentioned. So that's our digital threading technology. It's open source on GitHub. And then NRIC as a whole, we've open sourced all of our integrations. So NRIC, the versatile test reactor, the translational challenge reactor uses some of these tools and techniques at Oak Ridge. The strategic thermal irradiation capability. At NNSA, there's two projects. There's a digital engineering project, and there's a digital twin project as well. And then there's a number of smaller research projects internally to do like data warehousing for nuclear environments that are also use these techniques. But full digital twins, there's only a few of those that are really in thrust. And I will say we are kicking off full digital twin projects in earnest this year. So, but the main full one is the one you would have heard today in the breakout session number 2 if you attended. And if you didn't, there'll be a recording available afterwards that you can view. So. So is Jared back?
Can you hear me?
Yes. Hey, there
wow.
we go.
Amazing technology.
It is. All right. So Jared, try to keep it to 5 minutes if you can. No pressure. So
yeah.
We'll get to
so I guess I can't see my slides yet, but basically you could probably just skip to slide 9 out of the bunch because you guys covered a lot of model-based system engineering work already in Peter's discussion and some of the others. Note that I am not seeing any of my slides yet, so I'm kind of flying blind. Oh, there's the title slide. If we could skip to, I think, slide 9, actually, just go right through it. Save some time.
I think it's a few more slides in. Cheyenne can hear us.
You'll see a lot of the same things that you saw in other presentations. So I'll just talk about some of the model-based systems engineering work. What I see is that title slide say model-based systems engineering. Chris, can you confirm what it says?
Yeah, so now we're on the digital workflow is different from a document workflow. And we're looking at the very typical system block diagram with lines that you and I have seen a lot. So
yeah. So I think what I want to discuss, and I don't know if we went into a lot of detail on this, is that we try to differentiate the different parts of your engineering effort into requirements, functional design, and physical design. And I think the issue is that a lot of times engineers, we design with requirements, and we don't necessarily delve into other aspects of design in a different way. If we go to next slide, of kind of like what model-based might look like. Okay, are you seeing the next slide, similar but different?
Yep, moving from a document workflow to a digital workflow.
Yeah, so with a digital workflow requires different approaches to how you perform your design work. Traditionally, we use things like process flow diagrams, hyphen instrumentation diagrams, single line diagrams, et cetera, and that is kind of this hybrid of functional and physical design you're performing at the same time. And what happens is it's more of a spiral model than a waterfall model, and so you basically elaborate on the design continuously and build in increasing level of complexity and detail. But it doesn't necessarily separate your functional design from your physical design. Well, digital workflow kind of requires that you separate the two out. That in the functional design space or the functional analysis space, you have a pure play functional like block diagram. And so this is why we talk about things like state machine diagrams that would basically allow you to trace from one mode of operation or one state point of operation to another one. And it gives us a graphical model to express something that we usually do in like Excel tables or Word documents or something like that. So it's kind of convenient. Next slide, please. So you should be seeing what does a model-based solution actually look like, and I'll just tell you that it looks like a bunch of boxes and lines with some text in it. And I think someone mentioned this before too. It might have been Chris. But basically, this is what your models are going to look like in a model-based system engineering solution. Next slide, please. And I'll give you some examples. Do you see functional diagram 1 of 2?
Yep, we see 1 of 2. Yep.
Okay, right. Okay, so functional diagram 1 of 2 I'm showing is basically a diagram of how we're going to synthesize fuel salt for the molten chloride reactor experiment. Now, actually, this is for a microloop, so it's not actually the scale, and it's not the actual process. It's just kind of high level. But basically, you write a procedure, but you do it visually. And writing out the procedure visually lets you see things differently. You can parallelize tasks. You can create do loops where you repeat something 40 times or not. You can examine inputs, outputs, resources, etc. It allows you to like kind of visualize the process differently from if you just wrote a Word document procedure and tried to do that. Next slide, please. You should be seeing a state machine diagram. The title is Functional Diagram 2 of 2. Yep. I mentioned it earlier, but a state machine diagram is an excellent way to characterize how you're shifting from one mode of operation to another. And you think about it one way is that we have logic diagrams for INC, and this would be a good precursor for that, where you're saying if a transient event occurs, then I'm going to shift to a different operating mode or a different state, if you will, right? And so this is actually a visual representation of that. And you want to capture things like I'm going to test, start up, operate, maintain, decommission, etc. And what happens is we finish our functional design, we move into physical design. Next slide, please. And your physical diagrams are going to, again, look like a bunch of blocks and lines, but the blocks and lines are relevant because you're showing the big high-level systems, electrical system, your reactor system, your primary coolant, INC, and it lets you just start stacking those interfaces up, and it should be able to trace directly from your functional diagrams to your physical diagrams. Next slide, please. And from that stuff, we'll produce some type of reports, maybe an n-squared matrix, maybe something that looks akin to a Word document. But the key here is that you update a visual model, and it allows you to directly port that into a document. You don't have to do a lot of Visio work or anything like that. No screenshots. It literally is the model. My next few slides, if you want to go through those, I just want to give a highlight of other things we do at TerraPower. Something we've been pushing a lot is using computer software to develop reactors. So we've been doing maybe not some of the same work that INL's been doing, but we've been working a lot on the Army framework at TerraPower. Next slide. Should say TerraPower we have unique capabilities, but not fully integrated with model-based system engineering. We use a lot of tools to help design and develop our reactors, mostly for the sodium fast reactor. But one of the key challenges to digital engineering is integrating all these tools into a usable working model, not just at the conceptual level, but, moving towards that digital twin that other people are trying to implement. And if you go to our GitHub page for Army, you can actually read into some of the documentation. We open source part of the Army framework so that other people could plug into it and play with it and use it for their own purposes. And we're hopefully going to integrate using tools like deep links that INL is working on. I'm really going to try to use what INL is working on and try to build on top of that rather than try to go off on our own in a silo. Anyway, that's all I have for my presentation for now. I'll, of course, take questions if they come.
Okay, let's start with our first question on that note. So our first question, if we go back to the panel discussion slide, is do you foresee regulatory aspects of applying digital engineering in nuclear, and how do you plan to address those? So the first thing I'll mention with that note is NRIC is having initial discussions with NRC about digital engineering and how it can be used in the licensing approach in the future. And we think there's some promising aspects to that. But I'll kick it over to Jared. Have you seen similar discussions on your end?
You know what, from the regulatory side, I can't see a lot of issues because at the end of the day, you're still going to produce documentation that's going to have a very controlled baseline that you're going to control changes to. I think the outputs are very similar to what you see in existing industry. It's just that how we get up to that documentation point where we submit it to the regulator is different. It's more efficient and seamless, hopefully. So I've not seen any issues with that.
So Jared, there was a question earlier that I think would be interesting to get your opinion on, which is adopting digital ecosystems is hard. Employee pushback, lack of experience in leading digital transformation, and limited company budgets are kind of the norm here. So how is TerraPower tackling that issue?
I'll tell you first, I really think that it's going to be hard to roll it out to the full company without getting some management buy-in. So what you want to do is at least have your management say that, hey, digital ecosystems matter, and we want to do that. I think NRIC's done that, obviously. But you want to have a SWAT team, if you will, people that are very interested in that subject, that topic, and then try to think of how can I apply this at my company. So you want some people to be the spearhead, right? To kind of come up with the idea, come up with that concept of operations. How are we actually going to do that inside our company? And then propose that to your management team and proselytize that to your groups. A lot of the things we encounter is that people have a very set mental model of how engineering works, and they don't like it when someone upsets that. And nuclear, especially so, because we've been operating a light water reactor fleet for 67 years, and so anyway, yeah, I guess I would say get us a Tiger team, SWAT team, whatever you call it, people that are interested in doing this. Set up some of the infrastructure on a small project, and then try to scale it up to your bigger projects down the road. I think existing old projects are not going to try to integrate a lot of these tools unless it's easily affordable and available.
All right, thanks a lot, Jared. Okay. So we're at time. So I'd like to thank Mike and Jared for their time on this panel discussion, and all of our presenters today who did a great job giving a good brief on digital engineering. And I hope that some of you, after hearing this, are as excited about digital engineering as I am. So I thank you for attending our first NRIC Tech Talk. If you have ideas for future topics that you'd like us to follow up on, please feel free to email nric@inl.gov. NRIC is planning some specific regulatory topics relevant to demonstrations in the near future, and we'll also welcome your suggestions. So from everybody, thank you very much for attending, and we'll see you all real soon.